In this video, we'll talk about how we approach and solve related rates problems. So the process for solving these is basically the following. We need to find that equation that relates to two quantities we care about, and then differentiate to get a equation that relates the rates of change of those two things, and use that to solve our problem. So step one of the process is always draw a picture. If applicable, it usually is, so you should definitely try to draw a picture. Or if not a picture, at least a sort of diagram as to what's going on in the problem. What you'll want to do here is also label things in your picture that relate to this problem. So if something changes in time, you want to label it with a variable. If it does not change in time, you could either put a variable there or the actual number that it's fixed at for this problem. The next step is to use your picture and your geometric knowledge to figure out an equation that relates the two quantities or more that you care about in this problem, namely the ones whose rates you know and whose rates you don't know. And the main thing here is if you put a variable in this equation, make sure it's on your picture and you know something about how it's behaving. Next, you want to take your equation and differentiate it in time using implicit differentiation and the chain rule whenever there's something there that's changing in t. And this should give you the related rate equation you need that's going to tie the rates you know about to the rates you don't know about. And then finally, once you get to this step, you can now plug in the numbers in the problem, for instance the radius we had in the first example, to actually find your answer. To be careful, if you plug in numbers too early, you'll end up getting rid of variables that should have been there in your final answer, and then you differentiate and it goes away because you plugged in a number for it instead of leaving it as a variable in the first place. So you have to make sure you differentiate before you start plugging in numbers. Let's look at our example from last time and see what it looks like. Here's our same spherical balloon problem. Step one is draw a picture. It's a sphere. I have a radius r, and I know the equation I care about here is that the volume is 4/3 pi r cubed. This is the right equation I need because I'm given a fact about the rate of change of volume. dV dt is 4 cubic inches per second. And I want to know about the change in r. And the two variables that show up in my equation are v and r. So when I differentiate this, I will get an equation that connects the rate of change of volume to that of radius. Now we've got our equation. V equals 4/3 pi r cubed. Note I have not yet plugged in 6. I will do that later. I can now differentiate this in t, with the assumption that both v and r are changing in t, so they have derivatives when I take this derivative. Now, on the left, the derivative of v with respect to t is just dv dt, and this equals 4/3 pi. Differentiating r cubed in t, that's a chain rule. It's going to be a 3r squared times a dr dt. Simplifying this out, I get that dv dt equals 4 pi r squared dr dt. At this point, I'm in good shape. I can now start plugging in numbers. I know dv dt, that was in the problem statement. I was given a value for r in the problem statement, and I'm trying to solve for dr dt so I can work this out. Solving it out, dr dt is dv dt over 4 pi r squared. Since dv dt is 4 inches cubed per second, this becomes 4 inches cubed per second over 4 pi, r is at 6 inches squared. Calculate things out, this becomes a 1/36 pi inches per second. There's the process for how you solve related rates problems, an example of this being worked out. The important thing is to go through everything step by step in order and make sure you don't plug in numbers too early, because if you plug them in too early, you'll get rid of variables that should have been there, and it'll change how you get the final answer of your problem.